Hello, how you doing? It's Mike here, and in this video we're going to talk about one-to-one functions. And they are very interesting because they make a special relationship of a function and the inverse of that function. So if you think about a function, if we think about a function, we look at f of x, for example, equaling to x squared. We recognize this is a parabola that opens up, and he intersects the origin and continues on like that. So it's supposed to be symmetric on both sides of the y-axis. However, sometimes I can't draw that very well. So let me try that again. So let me see if I can do a little bit better. So this look, no, there we go. Something like this. So you look for symmetry along the y-axis. So it's parabola opening up and it looks something like this. So if I were to look at a point, for example, at a value of 1, at value of 1, if I plug that in, I'm going to get a value of positive 1. So we get this point here, 1, comma 1. If I look at this point, negative 1, then I also get that same exact point, negative 1, comma 1. So we recognize here that f of 1 equals to positive 1, and then f of negative 1 also equals to positive 1. So we can in essence say that f of 1 equals to f of negative 1. So this is a relationship of a function that is allowed. So there's nothing that's problematic with this. However, there's a specific type of function, and specifically, so I'm using the specific word a lot. There's a specific type of function which prevents this from occurring. And there's some really interesting characteristics about this function. But basically, we're going to talk about one-to-one functions. So one-to-one functions are a specific type of function. So let's go ahead and just rhyme off a little definition here that you might see to define a one-to-one function. One-to-one function. So let's go ahead and define a one-to-one function. So we'll say a function f of x is 1 to 1 on a domain D, if, and here's the interesting part, f of some value we'll call x1 does not equal to any other value x2. So f of 1 does not equal to f of x2 whenever x1 does not equal to x2. And this is going to be in that domain D, because sometimes we will restrict the domain and define a function over a domain such that it is one-to-one. And we do that a lot of times, especially when it comes to trigonometric functions. So we'll talk about that a little bit later, but basically what happens is that everything we did up here, everything we saw up here, this can't happen. So it says that in order for this to be one-to-one, this circumstance can't happen. The same value that you see on this value of the domain cannot equal to the functional value of this value. So f of 1 cannot equal to negative 1. But if we notice here, if we were to go ahead and say, you know what, I don't want to evaluate from negative infinity to positive infinity, I don't want to evaluate this entire interval. I only want to evaluate from 0 to positive infinity. So what does that do? That gets rid of this portion over here. So that gets rid of all of this over here. So basically we have just the 1/2 portion of the parabola. And now when we restricted the domain, there are no values that will equal each other on our domain. So there's no functional values that are equal. So here as we keep on increasing, then we keep on increasing on the y-axis. So there's no two values of our function. So f of 1 would never equal to f of 2. F of 2 would never equal to f of 3, and f of 1 would never equal to f of 3. So there's an infinite amount of combinations that would happen here because we restricted our domain. However, if we looked at the entire domain over the entire real number system, then this function would no longer be one-to-one. However, if we look at it and we restrict it to, for example, from 0 to infinity, then this function now is one-to-one. So there's a lot of times where we look at functions and we evaluate them over a specific interval such that they are one-to-one. And you're probably thinking to yourself, why does it matter? Why do we care about one-to-one functions? And that's a really good question, and we're going to get to that a little bit later in our next video. But now let's just talk about some examples. So let's go ahead and look at f of x. So let's look at f of x. F of x equals to square root of x. So if we look at this guy, this is the root function, the square root function. He looks something like this. So the one thing that we know about the square root of x is that the square root of x is monotonically increasing. It's monotonically increasing, which means it is always monotonically, just as a fast is a neat way of us saying mono means one, and tonicity, I believe, means direction. So monotonically increasing. So it is increasing in one direction. So we know this function is always going up. So no matter what I pick, what value I pick along the x-axis, and we keep going, is that we know no two values will equal each other. So f of 1 will never equal to f of 2. F of 2 never equals to f of 3. F of 1 never equals to f of 3. F of 1 never equals to f of 4, and so forth. So this function is continuously increasing. So now let's go ahead and look at another example. So let's go ahead and look at maybe sine of x. So let's go ahead and discuss g of x, and we'll call g of x. So we'll say this is equal to sine of x. So sine of x, hopefully we recognize these sinusoidal functions, is that they are always going to reoccur. So this right here is one period, and then look what happens again. Over the next period, we see it's going to have that same reoccurrence, that same motion, and it goes backwards as well. So this is another period. So we see here that this is a period. So this right here is going to be one period, and this is going to be one period, and then we see another period over here. So the period here is going to be a value of 2 pi. So every period here is a value of 2 pi, and this basically states that sine will reoccur every 2 pi. So the same function will repeat itself every value of 2 pi. So we can see clearly here that if I were to look at an example, of pi over 2, if I look over example of pi over 2, that at pi over 2 here, we equal to a value of 1, and this is 1 and negative 1. So here at f of pi over 2, we equal to 1. And then as we traverse this graph, that doesn't really show up very well. As we continue on, we see over here at some value over here, look what happens. We also equal to 1. But what is this value? If we take pi over 2 and we add a period of 2 pi, so this will be 2 pi as well. So if we take pi over 2 and add 2 pi, so pi over 2 plus 4 pi is over 2, which is an example of 2 pi, which is another way of writing 2 pi. This equals to 5 pi over 2. So this is going to be 5 pi over 2. So that question mark is 5 pi over 2. So we see that f of 5 pi over 2 is also equal to a value of 1. So that's supposed to be 5 pi over 2, not pi over 2. So 5 pi over 2 also equals to positive 1. So we see that f of pi over 2 equals to f of 5 pi over 2. I just can't write the 5 for some reason. And they both equal to 1. So two different values of x. So x1 does not equal to x2. However, f of x1 equals to f of x2. We could see that as a violation of this definition. So as we define this up here, x1 does not equal to x2. So we see that pi over 2 does not equal to 5 pi over 2. So pi over 2 does not equal to 5 pi over 2. However, in order to be 1-to-1, the functional values cannot equal each other. So f of pi over 2 would not be allowed to equal f of 5 pi's over 2. However, clearly here we see that they both equal to a value of 1. So we know sine of x, we can say, is not 1-to-1. It is not 1-to-1. But notice, if we were to restrict our sine curve, and let's go ahead and use a different color here. So I'm going to use maybe purple. So maybe let's look at purple. So if I were to look between, and that doesn't show up very well. Let's use yellow. We'll use yellow. So let's go ahead and say that let's say I restrict my sine curve, and I want to go from pi over 2 to 5 pi's over 2. So I'm just looking at this portion right here. So as I get past here, look what happens. All of a sudden, these two values will be equal, and these two values will be equal. So as I keep going, as soon as I hit past this apex, also known as a vertex, also known as a min or a trough, then all of a sudden we're going to have congruent values. So notice what happens here is that I form a horizontal line. And if I attach these 2 points, I see a horizontal line. And this is actually one of the ways that we can test. We can test for for one-to-one functions, and it's going to be called the horizontal line test. So sometimes we want to pick domains such that we know we're going to be guaranteed a one-to-one function. So let me go ahead and look at blue here. Notice here if I go from negative pi over 2 to positive pi over 2, which is this value right here. So I'm traveling from negative 1, and I keep going, and I keep going, and I keep going, all the way to this value up here. So I'm just going to draw our sine curve, and I'm just going to look, and I'm trying to shade in this portion of the curve, but for some reason it's not allowing me. And notice I travel, and I get that. So if we look at here, if I draw a horizontal line, anywhere through this portion, I hit the curve once. I hit the curve once. I hit the curve once. And I hit the curve once. And I never, ever, ever hit my curve twice. So we notice if we never hit the curve twice, if I draw my horizontal line, then I have a one-to-one function because this rule over here is not violated. So let's just talk about a quick graphical way, or maybe a visual way, to determine a one-to-one function. So we call this the horizontal line test. If a horizontal line can be drawn through a curve and it intersects at most one time. So that means it can't intersect 2 or 3 or 4, but it could intersect 0 or 1. The graph is a 1-to-1 function. So we can use this test to determine graphically whether or not we have a one-to-one function, because therefore we know if x1 does not equal to x2, we know that f of x1 would never equal to f of x2. So we know that we would not violate the constraints of the definition of a one-to-one function.